Hi, this is Naksai Krishna, studying ECE in VVIT from Section B, and my roll number is 20BQ1804C5. First, we discuss about origin of energy bands in crystalline solid, classification of solids based on energy bands, chemical bonds in semiconductors, intrinsic and extrinsic semiconductors, Fermi energy level, intrinsic carrier concentration, p-type and n-type carrier concentration, equation for conductivity, drift diffusion, and Einstein equation. First, we discuss about crystalline solids. The solids atoms are arranged in regular pattern. They have physical properties like conductivity, refractive index, velocity. Sound depends upon the direction. They have sharp and well defined freezing point. What is an amorphous solid? No regularity in the arrangement of atoms, isotropic in nature. They do not have well defined melting and freezing point. Now we discuss about origin of energy bands in crystalline solids, classification of solids based on energy. In an isolated atom, there are many energy levels such as 1s, 2s, 3s. They are occupied by the electrons. When isolated atoms are brought together to form a solid, various interactions occur between the neighboring atoms. During interaction, the higher energy levels are affected considerably, and consequently the energy levels of the outer shell are increased. Hence, simple energy levels of atom split into large number of energy levels as shown in the above diagram. Since there are many atoms in solid, so separation between split energy levels is very small. There are energy bands in a solid corresponding to the energy levels in an atom. An electron in a solid can have those discrete energies with these energy bands. These energy bands are also known as allowed energy bands, which are generally separated by some energy gap known as the forbidden energy bands or not allowed energy band. Energy band occupied the valence electron is known as valence band, and the energy band which is empty or occupied the conduction electrons is known as conduction band. As we shown in the figure, insulators, semiconductors, conductors. For insulators, the band gap is more than the gap between conduction band and valence band is more than we compare it to semiconductors and we compare it to conductors. Insulator. An insulator which does not allow the passage of electricity. An external electric field cannot provide this amount of energy to an electron in solid. In insulators, the valence electrons are bonded tightly to their parent atom. Therefore, such solid behave as insulators because of there are no free electrons or availability to conduct electricity. That's why they were called as insulators. Semiconductor. What is an semiconductor? Usually, we know that when an germanium or silicon atom is doped into a pure electron band, the energy band between filled valence bond and the empty conduction band is small as compared to the insulators and more as compared to the conductors. Germanium and silicon are the common examples of semiconductors. At 0 Kelvin temperature, semiconductor behave as an insulator, but room temperature semiconductor has the following properties: partially filled conduction band, partially filled valence bond, very narrow energy bond. In conductors, there are no gap between valence bond and conduction bond. Due to absence of this gap between conduction band and valence band, there is no chance of presence of holes. Hence, total current in conductors is simply due to flow of electrons only. There are sufficient number of free electrons are available for electrical conduction in conductor. That's why these materials are called conductors. Now we discuss about chemical bonds in semiconductors. After that, in intrinsic and extrinsic semiconductors. Semiconductors like germanium and silicon has crystalline structure. Both these materials are trivalent. Each has 4 valence electrons in outermost shell. When electron escapes from the covalent bond, an empty space is left, which is called as hole, or a hole is nothing but an positive charge. A semiconductor in which electrons and holes are created by the thermal excitation is called pure or intrinsic semiconductor. The electrons reaching the conduction band due to thermal excitation leave equal number of valences or holes in valence band. Extrinsic semiconductors. These electrical conductivity of pure germanium or silicon can be increased by adding impurity in the process of crystallization. The added impurity may be trivalent. The suitable pentavalent elements are phosphorus, arsenic, etc., whereas trivalent elements are boron, aluminum, and gallium, etc. Due to this type of impurity added, the extrinsic semiconductors can be divided into two types. There are N-type semiconductors and P-type semiconductors. N-type. When germanium is doped in with arsenic material, this type of doping takes place in N-type conductor. The resulting crystal is called N-type semiconductor. The fifth electron of arsenic atom is not covalent bonded, but it loses bound to the arsenic atom. Now, thus the arsenic atom contributes one conduction electron without creating a positive hole. Hence, arsenic is a donor element since it has free electrons. The crystal has a whole axis of electrons which are current carriers. Since current carriers are negatively charged particle, this type of semiconductor is called as N-type semiconductor. Now we discuss about P-type semiconductor. When a pure atom, let us say germanium atom, is doped with pure crystal or like a trivalent elements boron or aluminum, these type of semiconductors are also called as P-type semiconductors. Let us consider trivalent boron is added to pure germanium crystal. It steals one electron from the neighbor germanium atom due to insufficient of electron to get bonding with the germanium. There is one hole exists. This process continues and the hole moves in a random way due to thermal effects. Since character carriers are positively charged particles, this type of semiconductors is called as p-type semiconductor. Now we discuss about Fermi energy level. The energy level between the conduction band and valence band is known as Fermi energy level. The maximum energy level occupied by a particle at 0 Kelvin temperature is known as Fermi level. First, from figure A, we discuss about intrinsic semiconductors, B, N-type semiconductor, and C, P-type semiconductor. Intrinsic semiconductors, the Fermi energy level is